So, today I will discuss about the surface tension of a liquid. So, measurement of surface tension of a liquid. So, that is the experiments we will discuss, but before experiment we should know the working formula and how this working formula has come, how to derive it. So, that is what first I will discuss before demonstration of this experiment in our laboratory. So, measurement of surface tension of a liquid. Okay. So, when you will measure something, some parameters, so we use some method. Okay. There are different method one can use to measure that parameter, but we have to choose one particular method in our laboratory, and for that you have to develop the working formula or develop theory for that method. So, we will use this method that is called capillary rise method. So, basically by capillary rise method. Okay. So, for this method we have to find out the working formula. So, let us just discuss what is surface tension, what is the origin of this surface tension. Okay. So, if you just put a liquid, say mercury is a liquid heavy metal. If you put mercury on a glass plate, you see that it takes spherical shape. It is a spherical drops or spherical ball like things. If you put water on the glass plate, so generally it does not form the water droplets. Generally it spread over the glass plate. Okay. So, in one case you are seeing this, it is taking spherical shape, this mercury, whereas the water it is it spread over the glass. But if you put this water in on other surface, so there it may form the droplets, spherical droplets. Okay. So, so this is because of surface tension. So, different surface have different surface tension. So, for any system energy, the system try to keep the total energy minimum. So, if you put mercury on a glass plate, surface tension of mercury is very high than the surface tension of the glass plate. It is not all the time, it is surface tension is only exist for liquid. It's for any surface there is a surface tension. For solid also, that means for glass plate also this it has surface, so it has surface tension. Okay. So, this surface is basically that is the air and that material at the interface. Okay. It is that material is exposed to the air, material, the area of the material exposed to the air. So, that is the basically surface of that material, and now its energy will depend on the area of the surface. Okay. So, in case of mercury, surface tension is very high. glass surface tension is low compared to mercury. So, now when you put mercury on glass plate, if it spread over, so then area of the mercury surface will be whatever, so that will be higher than the surface of the mercury exposed to the air if it is in spherical form. Okay. Because spherical surface for same volume, spherical surface is always having the minimum area. So, that is why anything is try to take it in spherical shape. Okay. So, what is the definition of surface tension? So, surface tension is the definition is basically this force per unit length that is basically is force per unit length, that is the surface tension. Dyne, it is a dyne per centimeter or Newton per meter, that is the unit. So, this force basically is the tangential force on the surface of the liquid or any surface. Tangential, it is a if you have this surface, this tangential force. So, basically tangential force is not perpendicular force, is the tangential force. So, this is the F. Now, over the length, what is the length? So, this force acts over this length. So, if it is L, so this F by L, that is the definition of surface tension, okay, per unit length, force per unit length. So, if then obviously if surface area is more, so length will be also more, and it will be of course in different direction. So, net force will be, so one has to find out. So, this is the definition of surface tension. Now, for any surface there is a force, tangential force, and per unit length, for per unit length whatever the force, that is the surface tension, that is the definition. Now, total force you will find out this, that acting on this surface tangentially. So, that will be gamma into L. So, this is constant for a particular liquid or particular solid surface. Okay. So, now we will do experiment for measuring the surface tension. So, this method will use this capillary rise method. Capillary tube, you know, generally capillary tube, this tube have very small radius. This tube has a internal hole, and that has very small radius. So, radius is very small compared to length, very small compared to length. So, if you take a tube, okay, and if you put in water, just drop into water, partially drop. So, inside water is there. So, you know this water level we are expecting up to this, whatever the water level on this container. So, in tube also we expect this. So, if you take higher radius, so you will see this level, but if you just reduce the radius, smaller and smaller, okay, smaller and smaller. So, you are changing the radius, it is basically radius of this capillary tube. So, if it is smaller and smaller, then you will find out that it's this liquid is for smallest one, it will be, it is rising, liquid is up to this, and for other if this is the radius, then it will rise say I think it's smaller height up to this. So, this rise of the liquid in the capillary tube it's depend on the radius of the tube. If radius is higher, liquid height will be smaller and smaller. Now, next is when water will come off here. So, this surface is not flat, this surface is not flat. So, if I draw uh, in larger scale. So, the surface of the liquid, if you see, say the surface of the liquid is, in case of water of course, for different liquid it may be different, it can be other way also. So, the surface is like this. Okay. So, we assume that this is a spherical shape, semi-spherical. So, this radius is so this meniscus, we tell this is the meniscus. Okay. So, it will take this form, this meniscus form. Okay. So, it is a basically hemispherical shape. So, that means this liquid is rising this way, liquid is rising this way. Okay. Here you have container, here you have container. Okay. So, here now liquid is at height. If you take this bottom of this meniscus, if you take bottom of this meniscus, this, okay, and this is the level, this is the level. If this we take this height is h, and this the radius r, the it's equal to the tube, capillary tube radius is r. So, amount of water is on the at height h plus r, it is not exactly r. Okay. So, there we have to calculate what is the volume of this much, water. I think so. This the volume of water, this the volume of water. It is above the. Okay, what is the volume of this water? So, water is now above this level, So, now there will be gravitational force will act downwards, and there is something else force which is taking it up. So, whatever the addition this some force taking it off, which is balanced with this gravitational force of this liquid column. So, that will be balanced. Now, whatever this force which is taking up, that is basically nothing but the surface tension, Okay. So, as I told, the surface tension, it acts on the surface tangentially. So, this is the force will act. So, this force, let us tell this surface tension gamma, this force per unit length. So, if this contact, this called contact angle, this theta, this we tell contact angle, this theta. So, you can take two component of this force, one is vertical direction. So, that is gamma cos theta, and another is horizontal direction, that is gamma sin theta. So, this gamma sin theta basically is perpendicular to this surface, not to this surface, on this perpendicular to this vertical direction. So, this will be in all directions. So, that will be balanced, but this one vertical one is basically is the resultant force acting on this liquid, because of this vertical force that is coming due to the surface tension, because of this vertical force, this liquid is now going up. Now, that will be balanced by the gravitational force acting downwards. Okay. So, here this, what is the total force on this surface then? What is the total force acting on this surface? So, that is this, if the radius is r, this perimeter, it is acting as a on the perimeter. So, that is I think 2 pi, perimeter is 2 pi r, 2 pi r, this is the length, perimeter length, and then for this gamma cos theta, that is the vertical component per unit length, this force per unit length, vertical component of this gamma, of course. So, this will be the force, upward force due to the surface tension, and that will be balanced by the gravitational force, downward force. So, that is mh gravitational force. What is this gravitational force? That is mass, basically mg, that force. So, mass is, so this volume and this density of this liquid. So, if density of this liquid is rho into volume, volume of this water. So, what will be the volume of this water? So, basically for this one, this pi r square, okay, into this h, this okay. So, I will take h plus r, okay. If liquid is full up to this, so this is the volume, but this part is not, there is no liquid. So, I have to take minus of this volume. So, this volume is basically half of the sphere. So, sphere volume 4 by 3 pi r cube, then divide by 2. So, that will be the volume of this hemisphere here. So, into, of course, density has to be multiplied. So, from here, so this angle generally is theta is very small. Okay. So, then it is a tends to 0, if we take, then cos theta is 1. So, we will assume that theta is very small. So, then basically cos theta equal to 1, then you are getting 2 pi r gamma equal to, from here I can take pi r square, yes, pi r square, rho is there. So, inside there will be h plus r minus, here basically 2 by 3, 4 by 3 by 2. So, 2 by 3 r. So, 2 by 3 r. Okay. So, finally, what you are getting? You are getting this gamma equal to, so pi will go, r will go, and then this 2 is there. So, I will get rho r by 2, then h plus r by 3. Okay. So, this is the G is missing, it seems. So, that was the mass, and then this is the force. Now, this is basically mass, then I have to multiply G, So, there should be G, here, So, I got this G rho r H plus r by 3 divided by 2. So, this is my working formula for this capillary rise method. So, this is my working formula. Okay. Now, so finally, what I got? I got this working formula for capillary rise method, gamma equal to rho G r H plus r by 3 divided by 2, So, this is the working formula for this for the capillary rise method to measure the surface tension. So, in laboratory we will see the arrangement. Basically, in laboratory we will take three, we will take basically three capillary tube of different radius, and we will put in water. We will measure basically in laboratory we will demonstrate how to measure this surface tension of water. So, one can take soap water, one can take salt water. Okay. So, we will take this. So, here basically depending on R, H will vary. So, in our hand only we can vary the, for a particular liquid we can vary R, for different R H will be different. Okay. And so, this experiment will be repeated for different radius of the capillary tube. So, we will take 3 capillary tube having different radius, and we will do the experiment, and there you will see, as I mentioned. So, this kind of rise of the water you will see, Okay. So, now we have to measure the height, So, we will use one indicator, okay. It will touch the surface of the water here in the container, and we will use travelling microscope, basically microscope we will use, because without microscope it is difficult to see this one and this meniscus. So, we will use travelling microscope. So, travelling microscope has vertical scale as well as horizontal scale, So, in this case first we will set here. So, then using vertical scale we will measure this height, this reading, and we have to take this reading also. The difference of these two will be the age. Okay. So, for these 3 cases we have to measure H using the travelling microscope, and we can measure, we will measure the radius R also. We have to measure radius R of these 3 capillary tube. So, that also these 2 ways one can measure. So, that if you take tube, and then if you take this tube and then put some generally mercury, if you put mercury of length L, okay, and then volume of the mercury will be pi r square L into density of the mercury, Hg. Okay. So, that will be the mass. Okay. Now, you can take out this mercury and measure it. means it's what is the mass that you can measure using balance. Using balance you can measure. So, that is known, this density also known. L you have to, what is the length of, so few centimeter is generally taken. So, that also you can measure. You not measure, you have to take the measure this length using either meter scale or slide calipers. I think this using slide calipers will be difficult. You have to use meter scale. So, then from here this so experimentally you are measuring m, then L, then you can find out R. Okay. So, this is the one method we use to measure the R. Another method we will use this just travelling microscope. So, this travelling microscope has this you see this focused eyepiece is you can take in horizontal direction, also you can take in vertical direction. So, there is a movement option for movement. So, here this tube now we put in vertically, now we will take it just make it horizontal arrangement, okay, and then focus using this travelling microscope, and from there you will be able to see this hole. So, that cursor that you have to take two reading, basically putting cursor at this end what is the reading, and then shifting the cursor at this end what is the reading. So, difference of these two reading will give you the diameter. So, diameter half of the diameter will be radius. Okay. So, using travelling microscope also one can measure it. So, I think yeah. So, this is about the method of measuring surface tension in your laboratory. So, we know the working formula and what are the parameters we have to measure, that we know. Okay. So, I think in next class I will demonstrate in the laboratory how we are measuring the surface tension of water. Okay. So, thank you for your attention.